Hey everyone, welcome to Duodecimal Division. My name is Eric Larson, and in this video I am going to be introducing you to the dodecagon. Okay, so here it is. This is the pattern that we're going to be using to generate the diagram that then in itself generates all 360 degrees. So we're on the path towards creating a diagram that divides the circle up equally into 360 parts, and this is the geometric pattern that we're going to be using to help us create that diagram. So we're still in a process of comparing between base 10 and base 12, so we really know the difference as to, in a way, why this pattern has been unavailable to us, or why it's basically existed. There you are. It's just drawn on a graph paper, so it's on a Cartesian plane, but in this diagram there's no actual base defined. There's no line coming down that says where the 1 is. So at this point it's just a pattern. But it's a powerful pattern in that all of the lattice points, all of the points here that define the actual shape of each dodecagon are lattice points. So those are points where the horizontal and vertical lines are crossing each other. So it's a very easy pattern to plot out on the graph paper. And you can see the slopes are very easily defined. The distances are easy to measure. All of the sides of this dodecagon, this 12-sided shape, are the same length. And if you give this first dodecagon the perimeter of 1, then the next dodecagon has the perimeter of 2, and then 3, 4, 5. So each ring is larger by a scale of 1, basically. So that's the basics of this pattern. So what I want to do first is, again, just compare the differences between approaching this pattern from a base 10 perspective or a base 12 perspective. Basically, what does that look like when we define the 1 on the grid and the relationship to the 1, again, to the actual dodecagon, and how all these points line up that actually define the shape. So we'll start by looking at this exact same pattern on a base 10 grid. Okay, and so here is that dodecagon, exact same pattern on a base 10 grid. So you can see these are the lines that define the 1, 2, 3, 4 on the x-axis, and the 1, 2, 3, 4, 5 on the y-axis. And you can see where the points are that define the dodecagon, and the lattice points where the 1 and the 2 and 3 are all intersecting. So you can see how the two different patterns, the Cartesian plane itself and the dodecagon, how they line up. And you can see here in the center I've got a circle with the radius of 1 in base 10. It means basically there's 10 little squares between the center of the circle and its circumference. So the distance between this point here, the edge of the circle, its circumference, and this point here that defines the dodecagon on the x-axis, there's 3 little squares there. So 0.3 is the distance between the circle and the edge of the dodecagon along the x-axis. So basically that's it. Again, you can see how that all looks. So the dodecagon in relation to the base 10 grid. Okay, so this is where it's always sat if we were to kind of look for that pattern. The slope of this line, say, we would have to go over 1.2 and then up 0.7 to get to that point there. And then we go over again 1.2 and then up 0.7 for this point, and that's the slope of this line. This one is sort of similar but different. We go up 1.2 and then over 0.7, up 1.2 and over 0.7. That's the slope of that line. So those are the slopes of the lines. That's what the dodecagon looks like on a base 10 grid. So now we're going to look and see what it looks like on a base 12 grid. Okay, and so here we are with that same dodecagon pattern, exactly all lined up exactly the same on the graph paper. And now we have a base 12 grid. That means that the radius of this circle is 12 little squares. You can see now that the distance between the circumference of the circle, its edge, and the defining point here on the x-axis is just 0.1 instead of 0.3. You can see that these points here now, the defining points of the dodecagon, are landing. These points are landing on the 1, the 2, the 3 of the y-axis, and the 1, the 2, the 3, the 4 on the x-axis. So now this dodecagon pattern is really sitting securely or firmly placed, very well anchored on the base 12 grid, on the 1 and the 2 and the 3. So that makes a difference, because now the slope of this line is over 1 and up 0.7, or up 1 and over 0.7. So we have this quality of it just being 1. And that enables us to really establish a very solid pattern, because now no matter what length we go along the x-axis, we will always be able to go up a corresponding 0.7. And again, that 0.7 is a different sized unit in base 12 than it is in base 10. That's a smaller length, a shorter length than 0.7 in base 10. So again, although it seems like it's the same slope, because the 1 is different, in base 10 it was 1.2, so we were missing the 1 by a little bit. So again, it's the fact that it's lining up with the 1 that's really important. And again, I'll mention these triangles, how what makes these foundational is the fact that they have the sides of 1 in relation to the square root of 2, or 1, 2, square root of 3. So it's again the fact that one of the sides has a 1. So now we have another triangle here where the base is 1 and then up that 0.7. So that's what the dodecagon looks like in relation to the base 12 grid. And so just to really hammer home this point, because here I think it might also be a little bit misleading, because we're sticking to the same size decimal places and it seems like the 1 is what's moving. So we're going to go back to that really big grid of just 1 by 1, and I'm going to show you sort of overlapping the base 10 and base 12 grids. And again, look at this distance here. Basically the distance of this 45 degree angle, this is a 45 degree angle here, is 0.5 root 2. Okay, so that's the dimensions of the dodecagon. All the sides are the length of 0.5 root 2 on the graph paper. So it doesn't matter whether it was base 10 or base 12, the sections of dodecagon are 0.5 root 2. So now we're going to look at that really big square one more time. Okay, so here we have that large square again, where from this point here to that point in the corner there is the length of 1. So we have a square 1 by 1. And you can see there's two colors here. We have black lines and red lines. So the black lines is the base 12 grid, and the red lines is the base 10 grid. So the corner points are the same coordinates. We have x is 0 and the y is 1. Then here in the middle, the red is 0.5. We're counting over in base 10, 0.1, 0.2, 0.3, 0.4, 0.5. And the black is 0.6, 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. Okay, so our 1 is the same, and we have two different sized divisions of the 1. So now I have this length here, and I was telling you in the last portion that the length of the dodecagon was 0.5 root 2. So that's the length in base, well, it was the length either way, but we're going to say the length in base 12. So we have the black square. So from here, going at a 45 degree angle from this point here, 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so I'm going to put this stick down here like that, and you can see that fits perfectly. So we have this length of 0.5 root 2, and it fits inside the 1 by 1 square exactly from that point there to that point there. So those are points that are completely not attached to any of the base 10 divisions. You can see here's the base 10 points a little bit over there, and the base 10 points a little bit up here. So it just doesn't line up the same way. So this, and then the same length, I can take it, I can put it again on that point there down to this point here. I think you can still see that. It's just basically 0.1 over. So the coordinates of this point again was 1.1. Again, how that circle, we had a circle inside this with the radius of 1. The distance between the edge of that circle, the circumference, and the defining point of the dodecagon is 0.1. And again, this length of 0.5 root 2 is fitting and touching down on that point, which again is just a little bit in or offset from the 1.1 in base 10. So I hope that shows you. So if we went to 0.5 root 2 in base 10, it would be from here like the red squares, 1, 2, 3, 4, 5. So in the one, it would basically be creating a diamond shape, which was totally different than the dodecagon. Or if we wanted the dodecagon, it would have to be outside, and then that 0.5 root 2 would actually be bigger. It would be longer than the stick. So that's the real difference. The 0.5 root 2 in base 10 is a longer length than it is in base 12. So I hope you can see the real difference. Again, that's what I want to really drive home that point right now. The difference between base 10 and base 12 when approaching this geometric shape. The one, the shape, the ratio between the one and this pattern is different in base 10 and base 12. So that's basically it. You can explore that a little bit more in your mind, just to kind of wrap your mind around it and become familiar with that idea, because that's where we're going to start now. We're going to look at this dodecagon, at the math of its shape and its relation to the Cartesian plane and the circle with the radius of 1. That's going to be how we explore this pattern in base 12. So that's what we're going to do now. That was the introduction to this shape. In the next video, we're going to look at the distinctive lines and its relationship to the other degree lines and to the other triangles, the special right triangle and the 45-degree triangle and all that. We're going to now immerse ourselves in base 12 geometry and examine this pattern and see, well, I'm going to show you again how to generate this pattern that in itself generates 360 degrees. So that's our goal. That's what we're working towards. So now we're going to start that process. The next video, we're going to get into the numbers and the math and start building the diagram that generates 360 degrees. So I hope you can join me for that. Thanks for watching.